Hi everyone, I'm Yi-Peng. Today I will be summarizing our web development journey so far. To do this, I'm creating a mental map divided into three main functions: the client side, the communication layer, and the server side. This represents how modern web application function as a complete system. So here you can see we already have the three sections here. We will start from the left. We have the client side. This is where our building blocks live. So first, we will have the HTML. The HTML provides the structure, and we will have another thing that is CSS that define the styles. And then to bring this page to life, we will use the JavaScript, where we are using the ES6 version. All these elements will need to interact through DOM, document object model. So what we will put it at the bottom. When the browser loads the HTML, it creates a tree-like structure. Our JavaScript uses this DOM to dynamically update the UI based on the user actions. So we will also need to connect these together. Next, we will move on to the communication layer. When our JavaScript needs data, it triggers a fetch request. So here, this arrow, we will put the fetch request. This request will follow the HTTP protocol using methods like get or post. So we will need that here. HTML protocol like get, post, sorry. The data itself is packaged in JSON format. So we will copy this. Which is a lightweight standard that both the browser and the server can easily understand. Finally, we have the server side on the right. The request arrives at a specific API endpoint on our server. So we will put the description here. Request to endpoint. Node.js acts as our runtime engine, and the express.js is the framework we use to manage our server logic. So we will have it here. Sorry. Node.js plus express.js. If the request requires data, Express communicate with MongoDB, our NoSQL database, just as what we practice in Project 2. Then we will connect this to here. Once the task is done, the server sends a response back through our bridge. So here we will have the response sent back. Finally, the data returns to the client side to update the DOM. This completes the full request response cycle. Now we have the full map. Let's dive into the high-level details on each component in the next part. Okay, now zoom in on the client side. This is a layer that the user interact with directly. Our goal here is to create a seamless user experience by combining structure, style, and logic. The foundation start with HTML5. We emphasize semantic tags. Semantic tags. So instead of using generic containers, we use specific tags. For examples, nav for the navigation menu, main for the core content, an article for blog post or products. This is essential for SEO, helping the search engines index our site, and web accessibility, allowing screen readers to guide visually impaired users through the content hierarchy. Next, for styling, we use CSS and paired with the Bootstrap framework. In CSS, we master the box model, calculating the total size of an element by managing its padding, border, and margin. Then we layer Bootstrap's grid system by using utility classes like .call-md-6. We ensure our layout is responsive. This means the website automatically realigns itself when switching from a wide desktop monitor to a narrow mobile screen. The logic layer is powered by JavaScript version 6. We use modern features like arrow function to keep our code clean and template literals using backsticks to embed variables into string easily. The most critical part is DOM manipulation. JavaScript treats the HTML page as a tree of nodes. By selecting these nodes, we can update the UI instantly. This allows us to change text or colors without a full page refresh, making the app feel fast and modern. Next, we move to the communication bridge. This is the messenger that allows the front end to request data and the back end to provide it. Communication follows the HTTP protocol. We use HTTP verbs to define our intent, like get is for retrieving data, while post is for sending new information like a login form. After every request, the server returns a status code. Status code. A 200 means everything went perfectly. A 404 means the resource doesn't exist, and a 500 indicates a server-side error. These codes are the primary way developers debug the data flow. We handle these requests using the Fetch API. Let's type it here. It is built on a synchronicity. By using a sync and await keywords, we handle promises. This is a game changer because it allows the browser to wait for data in the background. The user can still scroll or click on other buttons while the data is loading, preventing the frozen feel of older websites. Finally, the result of a successful fetch request is JSON data. JSON organized data into simple key-value pairs. It is the industry standard because it's lightweight and natively understood by JavaScript, making data serialization, converting data into a string for transport incredibly fast. Before we go into the final section, it is important to understand that for fetch to be successful, it must interact with the third layer, the server side. So we will need to move this down. When Fetch sends a request, it is looking for a specific endpoint defined in express.js. The server then processes the request, perhaps looking to MongoDB, and sends the response back through the bridge. Without this interaction with the server side, the fetch request would fail or return an error, and we would never receive our JSON data. Finally, let's explore the server side, the brain of the application where all the heavy lifting and data storage happen. This is where the business logic lives and where our data is permanently secured. The Node.js provides the runtime environment that lets JavaScript run on the server. On top of it, we use Express.js to handle our routing. Think of the routes as the traffic controller of our backend. We define API endpoints where a specific URL path like /API/user. When the request hits an endpoint, Express execute the corresponding logic, such as verifying a user's password or fetching a profile, ensuring correct data is processed. And here we will have the middleware. A key feature of Express is middleware. Think of it as a security checkpoint or translator. For example, the express.json middleware intercepts the raw data string coming from the fetch request and parses it into a JavaScript object. This happens in the middle of the request arriving and the response being sent, allowing our server to actually read and understand the information we sent from the client. For data persistence, we use MongoDB, a NoSQL database. Unlike traditional tables, it stores data in flexible documents. We use MongoDB to perform CRUD operation. We use .find to read data, .insert one to save records, .delete one to remove them. This schema thus nature is powerful because it allows our database to grow, evolve alongside our application requirements. This completes the full three-tier cycle of our web architecture. Now that we have seen the overall architecture of my mental map, I want to zoom in on the vital part. How does data actually travel from the database to our screen? We're going to explore the fetch API and the sync await. These might sound like complex terms, but they are actually really essential, like the traffic rules of the web that allows our app to get data without freezing up. But before we learn the rules, we need to see what happens if we don't follow them. And that will bring us to the problem of blocking. Imagine you're at a coffee shop with only one barista, which is JavaScript here. If the first person in line orders a very complicated drink that takes 10 minutes to make, and the barista stops everything to wait for it to be done, the entire lines get stuck. In web development, we call this blocking. Just like the left-hand side examples here, the whole UI will freeze for 5 seconds until it finally gets the data. And when your website freezes, the buttons wouldn't click and the user gets frustrated. This is why we need asynchronous code. It's like the barista giving out the first person a buzzer and saying, "Go sit down, I will notify you when the drink is ready," while they continue serving the next customer. This will keep the line moving and the website smooth, so the user experience is better in this way. That buzzer the barista gave out has a special name in programming. We called it a promise. So here we will learn about what actually is a promise using the restaurant analogy. A promise is exactly what it sounds like. When you ask for data, JavaScript will say, I promise to come back and tell you the result later. While we wait, the state is pending. Eventually, that promise will lead to one of the two results. It's like either you get the food or you do not get the food while you have the buzzer. The first one is fulfilled, which means the success. We got the data, which is like the perfect scenario. But the other one will be rejected, which means a failure. Something went wrong, like a loss of internet connection or something else. As developers, our job is to write code that is ready for both of these outcomes. Once we get a successful promise, we are ready to see what's inside. But here is the most common trap for beginners like me, the two-step handshake. So, what does to await means? At first I ask, why do I need to use the keyword await twice? Look at these examples. The step one is to fetch. After this, we will receive a locked envelope, which contains the response. You can see the outside of the envelope. It says the set is 200, okay, but you can't really see what's the actual data yet. The step two is await on the JSON data. This is like opening the envelope because opening the envelope and reading the content also take a little bit of time. We have to await that step too. So remember, if you don't open the envelope, you can't use the data. Now, even though we understand the mechanics of this two-step process, we have to face a very real problem. The server still takes time. If we are performing this handshake in the background, what is the user actually seeing for those 5 seconds that we are waiting? Does async await magically make the await disappear? Sadly, the answer is no. Async await cannot speed up the internet or slow database. What it does is it changes how we wait. Without it, the 5 second is frozen wait. The user is locked out. By using async await, the 5 second is now the background wait. The user can still interact with the rest of the app while the data is traveling. That's why we still need loading states. Because even if the app isn't frozen, the user still needs to know what the background wait is happening. In professional apps, we use a boolean like it's loading. We set it to true before we fetch and false after we get the data. This allows us to show a loading spinner or skeleton screen. It tells the user, hey, I'm working on it. Just give me a second. This is a small detail, but it makes the app feel high quality and reliable to user. So, we have established what we are waiting in the background to keep the user happy. But how do we manage all this complex waiting? Starting the loader, fetching the data, opening the envelope, and stopping the loader without our code becoming a total mess. In the past, handling these steps involved very messy code that was hard to read. But today, we use async await. We call it synthetic sugar because it makes the code sweet and easy for humans to read. It allows us to write our data fetching steps in a straight line from top to bottom, just like a story. This makes it much easier to fix bugs and work with other teammates. Even with clean code, we have to be prepared for the unexpected. What if the internet actually cut off? What if it's some other error that we couldn't handle? We are not expecting. We should never assume the internet is perfect, like those kind of things. We use something called try and catch to protect our app. The try block is where we put our happy path code, the things we want them to happen. The catch block is our safety net. If the server crashes or the Wi-Fi drops, the app wouldn't just die with a white screen. Instead, it will jump to the catch block, allowing us to show the friendly message like, oops, please check your connection. So that way, the user wouldn't be leave alone without knowing like what's going on the page, that the page is not actually working. To summarize, we use a synchronous code to keep our UI smooth. We handle the promise timeline. We remember the two-step handshake to open our data. And we use try-catch to stay safe. Now that we understand the theory, it's time to see it in action. To truly understand why we need a sync and a wait, we must see what happens when we don't use it. I have built this browser arrays. The red button is a synchronize, which is blocking. The green button is asynchronize, which is non-blocking. Watch what happens when we click on the red button. Now look at my cursor. I can't highlight anything. Nothing is working. The browser is a zombie because of the main thread is 100% occupied by a heavy loop. To a user, this will look like the app is actually crashing. But there's something interesting. Let me refresh this page. If we click on the red button first, and then we click on the green button, nothing happened now, while the red is still running. It's because JavaScript is a single-threaded. My green click is stuck in the text queue, waiting for the red loop to finish. But after the red task is done, the green text will finally move to the main thread and start. This will prove that one bad piece of sync code can delay everything in your app. Let's refresh it again, and this time we only click on the green button. Notice the spinner, the 5-second wait is happening in the background. We can still highlight words to do everything. Because of this, the main thread is free. We can still do the scroll to do the interact. The app stays alive while the work happens elsewhere. Before we dive in the code, now let's see what happens to the web before we write anything to it. Let's refresh it. When we click on Get User Data, nothing happens. Now let's write the function. I will name it Fetch User Data. Notice I'm adding the async keyword here. This is crucial. It tells JavaScript that this function will perform tasks in the background, keeping our main thread open. Inside, I will get reference to our HTML elements, the status text, the content area, and our loading spinner, so we can update the UI dynamically. I will wrap our logic in a try block for safety. The very first step is to show the spinner. We want the user to know something is happening immediately. Dot display equal with clock status. This is the message that we wanted to print. And here we will add the line of await since we want the effect to show like more obviously, we want it to pause for a bit so we can demonstrate that we can actually highlight while it's still loading the data. Now it's the green button magic that we showed before. We will use a wait fetch. This line will send the request to a real online server at JSON placeholder. The await keyword is the hero here. It pauses this function but does not freeze the browser. This is why we can still highlight text while waiting. So let's type it out. Once the server respawned, we get an envelope, then we need to await again to parse it into JSON objects so we can read the user's information. Now we have the data. Where does the name come from? It's a property called data.name provided by the API that's displayed inside an A3 tag. First, we will update the message. So it will show. And then put the content. So since we used a try, we will still need a catch. If the internet fails, the catch block will handle the error gracefully. So here we should put the catch block. Finally, no matter what happens, we must hide the spinner. The task is complete. So here we'll type finally spinner dot style dot display equal to none. When we click on get user data, it's actually loading, and we can still highlight the word since we used a await, and now it will show us the name. So to conclude our midterm recap that's tied everything together, we started today with a problem, the blocking experience, and how browser raised the red button proved that synchronous tasks trap the main thread, turning our web app into a frozen zombie to a user that looks like a crash. Then we implemented the solution in our live coding session by using a sync and a wait. We achieved three things. One, responsiveness. We used the data fetching wait to the background, which is why I could still highlight text while loading the spinner was active. Clarity. We used a two-step handshake to fetch and parse JSON data from real server, showing how modern SAP handles live data. Resilience. Through try and catch, finally, we ensure that even if the network fails, the user is never left guessing. The goal of asynchronous JavaScript isn't just to fetch data, it's to ensure that the interaction between the user and the browser never breaks. This concludes my demonstration on async, await, and the event loop. Thank you all for listening.